So we would like to define the independence statement between two random variables when x and y are continuous. Now, if x and y are continuous random variables, and if they are independent, then they need to satisfy this equation for all possible x and y values. So the joint, instead of, now, if you check the condition of independence for discrete random variables, it says what? The joint probability mass function should be equal to the product of the marginal probability mass functions for all possible values of x and y for independence. Now, the same definition can be written for continuous random variables. The joint probability density function at any value, any couple of x and y values, should be equal to the product of the marginal probability density functions at those values. Okay, so if this equation holds for all possible values of x and y, then we say that they are independent. However, if for any two value, if for any two x and y value, if this equation does not hold, then we say that they are not independent. Now you may ask this question: in discrete random variables, we can show this equation holds for a countable number of cases. For example, if we have 3 values here and 3 values here, all we need to show that this equation holds or not, there are 9 cases here. There are 9 cases here. And in the previous question, there were 4 cases. But what we have is a countable number of cases here. However, because continuous random variables can take uncountably many possible values, my friends, are we going to show this equation holds or not for these countably many possible values? In fact, we are not, because these are given in the form of functions, right? And we can simply multiply the marginal probability density functions. And if the multiplication of the marginal PDFs gives us the joint PDF, then we can simply say in a single statement if they are independent or not. Now, you are going to understand that example here. So I'm just going to refer you to the question 6. In question 6 in this presentation file, we have the joint probability density function that belongs to random variables x and y. They are both continuous, and they are taking values between 0 and 1. And that joint probability density function was equal to 2 minus x minus y. Now we have computed their marginal PDFs. If you remember, the marginal PDF of x was equal to 3 over 2 minus x. And because the contribution of y is similar to the contribution of x in this function, and their domains are the same, the marginal PDF of y should be 3 over 2 minus y as well. Okay? Now the question is this: are x and y independent? And it is very easy to check. If you multiply the marginal PDF functions for x and y, and if you do not get the joint PDF, and in fact you do not get it, so the product of the marginal PDFs is a weird function like this. However, the joint PDF is a linear function, so this is nonlinear and this is linear. Because the product of the marginal PDFs is not equal to the joint PDF, we can simply say that x and y are not independent. The answer is that short. I mean, proving independence for continuous random variables is much more easier than proving independence for discrete random variables, because in the discrete random variables case, you need to check all of countable number of cases here. All of possible cases you need to check. However, for continuous random variables, you just need to compute the marginal PDFs. If the product of the marginal PDFs is equal to the joint PDF, then they are independent. However, if they are not independent. Okay, if the product is not equal to the joint PDF, then they are not independent.